Another shape that is part of the conics is hyperbolas. So the definition is the set of all points in which the difference of the distances from two fixed points, called foci, is constant. If you recall, that's similar to the definition of the ellipse, except with the ellipse it was that the sum of the distance from the two fixed points was the same. Now it's the difference of the distance from the 2 points is constant. So that's the big difference. Ellipse, the sum is the same. Hyperbola, the difference is the same. Now the center is actually not inside of a round shape like it was with ellipse and with circle. Instead, the center is the midpoint of the line segment whose endpoints are the foci. And you'll see pictures of it on the next slide. Just gotta get these definitions out of the way first. And the vertices are the point on each branch of the hyperbola that are nearest the center. So if you look at these pictures over on the right hand side, you can see the vertices are similar to the vertex of a parabola. Now, these aren't parabola in one sense, because if you look at the ones on the it didn't work like I thought. This is what I need. Here we go. Okay, look at this one. Those are not parabolas because they're horizontal, and also because there's two of them. And the ones down here, sorry, my magic pen's not working well. There we go. The ones down here, it wouldn't be a function because there's two of them. They're on top of each other. So it's not exactly a parabola here we're talking about, but they are similar shapes. So the vertex of what we think of as a parabola is also where the vertices of the hyperbola are. And you can see the definitions here. Now there are a few other pieces we could do, but for the purpose of my class, all we're doing with the hyperbola is what you'll see in this presentation. I do less with it than I do with some of the other shapes. So you can see here the definition, or excuse me, the general equation, the standard equation for a hyperbola. You notice again that's similar to that of an ellipse, but I know this is going to be shocking, but an ellipse, the sum was the same, and its equation had the two pieces added together. Here, the difference is the same, and it has a subtraction in between the two pieces. So that part kind of makes sense. And which term is first? Whether the term with x is first or the term with y the term with y is first does affect the shape. So up top we have the one where I would say the two are horizontal. They're pointing left and right. That's what happens when the term that has x in it is first. And the one down lower, sorry about that. That didn't go where I wanted it to. Let's try this again. There we go. But the one where the hyperbola is facing up and down, that's when the term with y is first. So you'll notice also how to find the vertices is different based on each one, because on the top one, we'll need to use the number under the x term and add it to the x's of the center to get the vertice. The center is hk, just like it has been in the others. So the center is hk. It's the same with ellipse and circles, where we are looking at what's being subtracted from the x and what's being subtracted from the y to find the center. So that part's the same as other shapes. Then to get the vertices, if x is the first term, we will add and subtract a to the x value. If y is the first term, we'll add and subtract a to the y value down here in the vertices. And notice, with this, a squared is the first number. With some other ones, it had to do with which one is bigger, things like that. With this one, it's about which one is positive, which is almost always going to be the one that's first. I mean, they could write these in the backwards order and put the negative one first, but they almost never do. So a squared is really the first number, or the one whose term is positive. Like if you look at the blue equation you can see right now. The term that has y in it is positive, but because of the subtraction, the term that has x in it is negative. So we know that a squared is the number under the y because the term with y is the first one, but more importantly, it's the one that is positive. So let's try some out. Find the center and find the vertices. So again, like I think I brought up in the ellipse videos, you do need to make sure when you're doing the center that you're paying attention to the order you put things in. Because it would be easy for us when we do the center to look at this and say, alright, I see that +4, so that's a -4. I see the -2, so that's a 2. But that's wrong, because we just pulled from the y first and the x second. And we never do that. It's always x first and y second. So instead, we got to make sure when we're writing the center, we do look at the x value first. So we look over here. We're subtracting 2, so the center is 2, -4. Okay, now to find the vertices, we need to find a squared. A squared is with the first term, the one that's positive. So this is a squared. A squared is 36. So a is 6. And you can just remember it this way. Whatever term a is with, it's that variable that we're going to add and subtract the a to. So I need to just add a and subtract a from the y value. So -4 minus 6 is -10. -4 plus 6 is 2. So those would be the two vertices. So just to make sure the process makes sense, I'm looking for the first term, the term that is positive. The denominator is my a squared. I then find a, and I add and subtract that number to whatever variable is in that term in the center. Okay, same instructions here. Find the center and find the vertices. This time, for the center, we're going to have -7 coming from right here. We're subtracting a -7. That's why it's +7. And subtracting 1, so it's -7, 1. That is the center. Okay, now here is where we get a squared, because that's the term that's positive. It's also the first term. So this time a is going to be the square root of 7. And for my class, please leave it as the square root of 7. Don't give me the decimal. We want to leave it exact, so we're going to leave it as the square root of 7. Now this time, a is in the same term as the x value. So to find the vertices, I need to subtract the value of a from the x value and add it. So I'll do -7 minus the square root of 7 and -7 plus the square root of 7. Sorry about that. So again, you see where the a squared is located makes a difference in how you find the vertices. In this example, a squared was underneath the term that has x in it. So we add and subtracted that a value to the x. Back here, it was underneath the term that had y, so we add and subtracted the a value to the y. So that's all we do to find the center in the vertices. And just a reminder, for ellipses, a squared is always the bigger number. For hyperbolas, a squared is always the first number. So with ellipses, picking a is about size. For hyperbola, picking a is about location. And that concludes all we are doing with hyperbolas.